once again that is we will learn it, so don't worry even if you have missed the first class. So let us first denote the basic formulas, okay? So we are learning test plan analysis for API systems, right? What is the motivation? Because after that, that is we will apply that one for the stability analysis of nonlinear systems, okay? You can ask that is, this is linear, and then how could you just directly apply it for the nonlinear? Okay, for the linearized one, okay? That is when you have a nonlinear system, then already that is we have learned a bit, that is we can expand the function in Euler series, right? And from that is we can get a approximated version of the whole nonlinear system, but approximated with respect to a particular operating point, right? And then when you linearize and you have then ABCD matrices, I mean I'm at this moment we are interested for the unfold system. So suppose if you have x dot equals to f of x, then from that is you can get even you can write a star because last day I. Okay, so this is the original nonlinear system. This is the linearized one with respect to an equilibrium point. Suppose x equals to x star. This is the variable. Okay, that means it is a linearized version. Of course, I cannot use the same x. That's why there is last day also I told we cannot use the same x variable. We need to take another one. We discussed an example. Suppose that is if it is a parabolic expression x and fx, then with respect to this point so this is the operating point x star with respect to which we are linearizing. So the whole, instead of the whole nonlinear curve, we are now bothered about only this zone, right? This is the linearized zone. And now this expression that will express the behavior of the system only about this part. That is the concept, okay? Now if you change that x star, suppose if it is here or if it is here, similarly you will be getting a linearized zone. Okay? So now what will happen? This A star will give you some equilibrium points, okay? From this A star, of course the eigenvalues will be your equilibrium points. And now with respect to each of the equilibrium points, you have to analyze the stability properties, applying this phase split technique. That is the overall picture, okay? So we are building the theory, or we are learning the phase split analysis for API systems with the notion that finally we are going to apply it for studying the stability behavior of nonlinear system. And as you know, that is in case of nonlinear system, it is we have multiple isolated equilibrium points. I should not say that if we have, like there is a high possibility there is many of the nonlinear systems will have multiple isolated equilibrium points. So you have to analyze the stability of each of the equilibrium points, okay? Now that is coming to the linearization, that is it may, of course, it may happen that is if the nonlinearity is very peculiar, that is we are not able to handle the nonlinearity at the first time, then that is you first, like at the very beginning you linearize it, or else that is suppose you have that, or you with even with respect to the nonlinear system also, that is without linearizing, there also like for finding out the equilibrium points, what you can generally, what do you do? That is it A star. What is this A star? Del f del x evaluated at x equals to x star, right? So that is the concept of Jacobi linearization, right? Which is the core is this Taylor series expansion. That is one day, I believe that last week, that is I showed a little bit, although that is we haven't yet formally learned Taylor series. Depending upon that, you could remember that is I only wrote that expansion, right? So from that, there is a A star equal to del x at S equals to A star. So then that is, say for example, you have x dot equals to minus x square, or it may be minus x cube, or some other functions as well. So this is just arbitrarily I have considered an example. If the situation is something like that, or even that is when we learn the bifurcation, they are also, that is we use this kind of thing, that is x1 dot equals to, what was the function? That is mu, what was that? x1 minus mu x1 cube minus x1. What was that? The first one we learned mu x1 minus x1 cube, right? And then x2 dot equals to minus x1 or minus x2. Minus x2. And this is another example. So from that, that is like why is that is bringing this, so that you can have already those ideas that's embedded in your mind, that is for which, like what is the purpose for which we are learning the phase plane analysis. That is basically required when we discuss this bifurcation. Although that is just to we didn't so far we haven't yet learned bifurcation in detail. That is when I started. It was just to just give you the feeling, or it was just to make you familiarized with the phenomena, with this particular phenomena bifurcation. That we have already learned. If there is a parameter, then what happens? That is the equilibrium points that can change. Not only the equilibrium points, their stability properties as well. So I believe that is we consider two examples. In one case, we have seen that is if the region of mu changes, then the stability property of the equilibrium point changes. And then the next day, we got another example where it is we saw that the number of equilibrium point can also change, right? Especially for the other example, we saw that is for the positive range of mu, there was only one equilibrium point, or for the negative range of mu, there would be three, right? Say something like that. Can you all relate? So this, I believe this was the first example, right? And there was another one. If you just check for the time being, for the first example, you will find that is it has two equilibrium points. One of them is stable node or unstable node, another one is the saddle point. But that property doesn't remain the same. Right? So if this is the first example, that is what were the equilibrium points? One is 0, 0, another one is mu comma 0, right? So one is 0, 0, another one is mu comma 0. What was the property for 0, 0? Actually, see that this one doesn't depend upon mu, right? So whether mu positive or negative, its stability property will not change. So what was that? It was stable node or unstable node or saddle? No, that is when you first got the Jacobian matrix, and then that is you found the Jacobian by putting x star equal to 0, 0. Then from that, what was that A matrix? That is, what was the nature? In that case, what was the matrix? Oh, it had mu. Oh, okay. Sorry, I forgot. Mu? Minus 1. Okay. And second case? Minus mu? Okay. Sorry, I forgot. Sorry. So this is the first equilibrium point. This is the second equilibrium point.
Square. X1 is square.
Okay. I think in the second example we had Q.
Nothing. Second one was nothing.
Okay. So in this case, if you see, that is for the positive range of mu. That is, if mu is positive, what will happen? It's a saddle point, right? or rather at this moment we haven't yet learned saddle point, but anyway, one eigenvalue would be positive, one negative, so unstable, right? So for mu greater than 0, just as of now I am writing saddle point because the saddle one is now we are now going to learn. Saddle point means that is if one of the eigenvalue is positive, another one is negative, but none of them is 0. In that case it is a saddle point, but the nature is unstable, okay? But if it is minus for mu less than 0, then what will happen? That is, it will be a stable node. Stable node we have learned already, right? Now you see, that is what happens, that is it has a parameter, okay, in the system. So for one range, it's a stable equilibrium point, but for the other range, it's unstable. Like for the positive range, it's a saddle point whose nature is unstable. For the negative range, it's stable node. That is the meaning of bifurcation. That is, there is a parameter. Now the stability property of the system, it depends upon a parameter. So that is called the bifurcation, okay? And even that is, we drew the bifurcation diagram. That means if you draw the equilibrium point, if it is mu versus x1 star, that also we have seen, that is we drew one or two bifurcation diagram. That means at the 0 point, that is when mu equals to 0, then that is in one section or it is in one part the nature is something and in the other part the nature is something. Bifurcation in the sense as if after crossing that point, as if that is a boundary point, after crossing that the properties entirely changes, okay? So that's why it is called bifurcation. So effect of bifurcation, that is once of course the stability property will change, and at the same time in few cases the number of equilibrium point can also change. So to give you that example, I took the undamped damping equation, right? In case of undamped damping equation, if you see, that is for the positive range of mu, we had only one equilibrium point, or maybe for the negative range of mu, I am not exactly remembering. For positive range, we had only 0, 0, right? But if mu is negative, then we got 3 equilibrium points. One is 0, 0 and plus minus root over mu comma 0, right? So for the negative range of mu, there are 3 equilibrium points. However, for positive mu, there is only one equilibrium point. So from these two examples, we could see that is bifurcation doesn't only mean that the stability property will change depending upon a parameter, but number of equilibrium points can also change, okay? So in that and later we will learn the bifurcation in detail. So few of the pattern is that one is transcritical bifurcation, pitchfork bifurcation, another one is Hopf bifurcation, another one is saddle node bifurcation, etc. We will learn in detail, and just keeping that in mind, the other day I asked you to take the Xerox from the Khalid's Indian edition book where the bifurcation is discussed, although not in super detail, but still there is all the patterns and the related theory is there. We will take up all the, for in this each of these cases I will show you, we will take up individual examples to discuss the cases, okay? So this one actually corresponds to the first one, transcritical bifurcation, and the pattern is something like that. I believe there is I drew it, right? If this is mu, if this is x1 star, then you can see this is a straight line. What is the equation of the straight line? That is basically x1 star equals to mu. This part is continuous line, okay? The continuous line in the sense that is, this is for the stable part. You see, that is here for mu less than 0, it's a stable node. And then your x1 equals x1 star equals to minus mu, isn't it? So no, that is in this case. Here if you see mu 0, so this is my equilibrium point 1, this is my equilibrium 0.1, this is my equilibrium point 2. So in that case, it is 0, 0 means x1 star comma x2 star. That is my equilibrium point always. In all these cases, you will find that is one of them is 0, another one is varying. That's why we are able to plot it. But now, if it happens that is both of them are non-zero, then we'll have to draw two bifurcation diagrams, or you will have to take the help of a 3D picture. At this moment, we have two axes, right? It's a 2D plot. So that's why one is mu, of course the parameter, and another one is the x1 star or x2 star, which is varying depending upon the mu. But now if it happens that is both x1 star and x2 star, they are function of mu, then of course I cannot accommodate it in a 2D graph. Then either you have to take a 3D graph, or else if they are independent, you have to draw two bifurcation diagrams, okay? Now, as of now, that is if you see, that is for the second 0, 0, so the 0, 0 means x1 star equals to 0, then that is this part I can draw with dotted. Dotted in the sense that is x1 star equals to 0 for mu greater than 0, that is all this entirely section that is mu greater than 0 and all this section starting from here, it is mu less than 0. Now you see the first equilibrium point, x star equals to 0, that is unstable for positive mu, right? So here the unstable part I have drawn by dotted line, and continuous thick line means that is stable. So x1 star equals to 0, that is unstable for mu greater than 0. So that's why this part I have drawn by dotted. Whereas interestingly, for the same positive range of mu, the other equilibrium point x1 star equals to minus mu, that is stable node, isn't it? So that's why this part is not dotted line, this part is a thick line, x1 star equals to mu. And then on the other hand, the same x1 star equals to mu for the mu less than 0. What would happen? Then it would become a saddle point, which is unstable, right? That is here, what will happen? For the second case, if you mu greater than 0, then stable mu. If mu less than 0, then minus of minus plus, so then it would be a saddle point, which is unstable. So completely the opposite type of nature, right? So that's why x star equals to mu for mu negative. This I have drawn by this dotted line, okay? But at the same time, x1 dot equals to 0 for mu less than 0. That you see I have drawn by a thick line because that is stable node. So this, the center point, I mean where mu equals to 0, that is the point of bifurcation. That means that is as if that is the border point or border line. In one side the nature is something else, in the other side the nature is completely opposite. Okay? That is the meaning of bifurcation. And this point is called the critical point or the bifurcation point. The concept, this bifurcation, it is something like that. At this moment you might think it is completely a new concept, but the pattern is not new to us. If you think about the root locus, when we had k by s plus 1 into s plus 3, it's a very standard example for root locus. Can anybody tell me that is what is the pattern? What is the pattern? It would be a part of the branch. In this portion, it is not. Here you will have two branches. One will be going this side, another one will approach from this side. After that, there will be a breakaway, right? Something like that. Although my drawing is really bad, but still it will be something like this. Do you agree? Now, what about this point? This is the boundary point. We call it is a critical point where K equals to K critical. What does it mean? That is, in the closed loop system, if you make this K equals to K critical, then you will be getting a complex conjugate pole pair. So in the closed loop for K equals to K critical, you will have a purely, that is, complex pole on the imaginary axis. So it will be then, that is, if it is, and this point is also the point of sustained oscillation, right? So this is also something like that. It is just an analogy. Otherwise, no relation. It is bifurcation and it is a root-locus diagram. But to just give you the concept of boundary point, I wanted to recall this. That is, K is the critical point in which sense? If K is less than K critical, then it is in a closed loop stable. But if K is greater than K critical, then unstable. Here also the same thing. That is, if mu is positive, then one nature, it may be either stable or unstable, and for the opposite side, it will be completely the opposite nature, isn't it? This, you see, both of these equilibrium point, for positive range it is unstable. It's for the first one, for positive range it is unstable saddle point, for the negative range it is stable. So completely the abrupt change. And for the second equilibrium point also, for positive range it is stable, for the negative range it is unstable. Exactly similar to this. That is, at the point of K critical, where if K is less than K critical, then it would be closed loop stable. If K is more than K critical, then it would be unstable. So you can, that is, consider this analogy to remember. Okay? That is what will be J. So we can write J omega C minus J omega C. So this is the thing that is we were talking about, and this will be the application. Okay. Now can you understand that is we are learning for the LTI systems, but ultimately we will apply to the nonlinear systems. Of course, it is restricted to second order. We cannot apply the same for the third order or higher, up to second order only. But even up to second order, it is a powerful analysis. Why? Because here you don't have to find the actual solution of the nonlinear differential equation. That's why many times I said that it's a qualitative approach, not a quantitative. Quantitative means when you are finding out the actual solution of the differential equation, you are either plotting the graph or you are checking the individual terms in the solution, and then you are deciding the stability. But here we all know that is the solving a nonlinear differential equation is not an easy task. So that's why instead of finding the actual solution, qualitatively we are finding out the stability properties of the equilibrium points of nonlinear system, and of course with respect to some operating points, because once again, that is, I repeat, for nonlinear systems you cannot readily comment about its stability as a whole. Please be very careful about that. Once again, as for the linear system, we always ask or say this is stable or unstable. I mean either asymptotically stable or unstable or marginally stable. Never, that is, we were worried about the zone of the initial condition or else upon anything else, right? But please be careful, for nonlinear systems we cannot comment about the stability as a whole. Even if it is unstable, but that is also local in nature. You see, in this case, the saddle point is unstable, but if the mu, the zone is different, then it can change. So that's why when we deal with nonlinear systems, that is, first of all, you may have now more than one isolated equilibrium points. You have to analyze the stability with respect to each of those equilibrium points. And secondly, that is, we cannot readily comment about the global stability. In most of the cases, it is local. Local in the sense, it depends upon the zone of the initial condition, which we call the region of attraction. Okay, is it fine? Because the last day, that is, when she asked, Konika asked me that, sir, if we have multiple equilibrium point, then what will be the situation? That is, I then showed you, that is in the Khalil's book or even in Slotting book also, the phase plane diagram of the simple pendulum is there. If you see, there the 0, 0 is a stable focus. After that, plus minus pi comma 0, both of them saddle points, so unstable. After that, plus minus 2 pi comma 0, they are again stable focus. So even now also, if you see that one, then you will find that it completely depends upon the initial condition. Okay? So that's why if you have to analyze the stability of the nonlinear system, then first of all you have to find out the equilibrium points, okay? Then you find out the Jacobian, that means we are linearizing the system. Then you find out the Jacobian means, of course, this is the one, that is del x at x equals to x star. So it is the same thing I am denoting by J. Now with respect to each equilibrium point, there will be J1, J2, so on, and then you analyze the stability of each one of them, J1, J2, J3, okay? And that too is local in nature, okay? Is it fine? Now that is, I am going back to our. So why I brought all of a sudden, like I didn't plan to, but still I felt like discussing this bifurcation example once again, so that is you get a specific example or the situation for which we are learning phase plane. Because at this moment we are building everything for LTI. You may easily, that is, have a feeling that is ultimately it is a nonlinear analysis. So why should we learn for LTI systems? But this is the application. Okay, so that's why that is I thought of recalling this bifurcation example, so that readily you can relate that this is the thing we are going to do. In fact, last week when we discussed this example, at that time I mentioned that is after learning the phase plane analysis, you will have a complete graph about this. That is, how did you do? But now I think you can relate. Although the saddle point we are about to learn, but at least the stable node we have already learned. Stable node and unstable node, right? So this is the application for any kind of second order nonlinear systems. That will be our advantage once you know the phase plane analysis. Okay? You check your notes. If you have any doubt, you can ask.
So,
Yes.
when we are designing a controller, in this case, the controller will work locally to that particular equilibrium, so the point which we are working on, or it will be global.
No, all of them are local.
No, the controller which we are designing for one particular point,
Huh.
particular forced equilibrium point.
Huh.
So that controller will work only in certain range of that equilibrium.
Of course, that it will be for certain range, because the controller that you will have, you understood what he has asked. That is, we have the stability properties, they are local. I said you have also, that is now understood. Now the next question is that when we will design a controller, then will that be also local in nature or global? Yes, that will also be local, because suppose you have linearized a nonlinear system with respect to an operating point. Now you have a linear one. Okay, so say for example this one x a star, and at the same time you have some b star u star, okay, or u star, that is u tilde. Then suppose you are using an LQR controller, even there is any other thing, even the PID also. Of course, now that is like meant for that linearized one. So and now during this operation, I mean like during the experiment, if the, I mean like when the system is running, if that operating point shifts too much, then of course the capacity of the accuracy of the controller will degrade. And that is the reason why we learn robust controller. I believe those who have attended my robust controller, there we were discussing that point. That is like that when we deal with such kind of systems, even for not only for non-linear, even in case of linear also it can happen. That is, suppose with respect to, it may not happen, that it may not be possible, that is for one controller to maintain the same accuracy or to give the same performance for the entire region. So it will be of course local in nature, and because but at the same time what can happen, that is depending upon the parameter uncertainty or even disturbances or change in the operating condition, the operating point will shift. And as you know, that is, it is the local model. So if the operating point changes, then along with that A star or the Jacobian will also change. But the controller is a fixed structure controller. We have designed with respect to a particular A star. Then what will happen? That is, of course, the performance will degrade. And that is the requirement why we go for robust controller. Robust controller means if for a region of variation, it will try to manage. Even if the operating point changes, of course, you cannot guarantee, or you have to like bind it within a specific bound. That means if the when we are designing when we design a robust controller, that is, you have to then always specify a bound of variation. You cannot expect that is okay, whatever may be the variation, 5%, 8%, 10%, 15%, the robust controller will be a superpower controller, it can handle anything. It is not at all. So of course there will be a certain parameterization, and with respect to a certain bound, that is, if we can design the controller properly, it will handle. But again, unfortunately, if the variation is beyond that considered range, then again the controller will like lose its accuracy.
So practically speaking, so controller should have this aspect of the range in which it will work, right? So is there any mathematical tool which will give us the insight on the range of the operating?
The same thing, that is the region of attraction, that we will learn when we will like start the Lyapunov analysis. Then from that only, that is, we can find out what is the region of attraction, and accordingly we decide everything. That is a very important aspect for nonlinear system. For LTI, we never had to think about all these aspects, but for nonlinear, they are really important ones. Okay, then from x dot equals to ax, although that is given only, that is what we use, x equals to pz, and then we got z dot equals to a bar z, right? Isn't it? So both x and z, they belong to 2 cross 1. Now what was the equation that is we learned, and in that case basically you have z1 dot equals to lambda 1 z1, or rather I should not say because it has 3 structures, right? Last day, if you remember, that is in one case there are mainly 3 type of structures, right? One is the lambda 1 0 lambda 2, another one is lambda 0 lambda, this is k, where k can be either 0 or 1, it's a Jordan canonical form. And then another one is the complex conjugate eigenvalues, for which we had alpha minus beta plus alpha. So these 3 structures, 1, it is 2, it is 3. 1 we have already done. Today we will learn basically the second one, but it's one variation, that is if they are of different sign. Okay, that one we are now going to learn, and then after that the second one. Okay. So once again, that is if I list down the major equations, then your x z1t, that will be e to the power lambda 1 t z10. Any mistake or any mistake? Okay. So z1 and then z2t, that is any mistake? Are you talking about the sign? But I haven't used sign, only lambda 1 lambda 2. Then third one, that is z2 equals to Cz1 to the power lambda 2 by lambda 1, where C equals to Z20 divided by Z10 to the power lambda 2 by lambda 1. That is, this must exist, right? I am writing it belongs to R. And then what about the slope? dz2 dz1, that is C into lambda 2 by lambda 1, then z1 to the power lambda 2 by lambda 1 minus 1, isn't it? All this for when we learn the stable node, then that is we consider several numerical examples, right? Not examples, basically it is if you consider a few values, a few set of values for lambda 1, lambda 2, then what did we see? Is z2 equals to either z1 square or z1 cube, z1 to the power 4, right? From that you can easily predict the nature as a shape, right? And now exactly in the same way we will check, because now that is what is the case. That is the case we are going to deal with. Okay, so let lambda 1 equals to minus 1, however lambda 2 equals to plus 2, and for simplicity I am assuming C equals to 1. If that is the case, then what will happen? Z2 equals to Z1 to the power minus of, isn't it? So 1 by Z1 square. That is the situation for us, isn't it? Earlier we had Z2 equals to Z1 square, but now you see it is 1 by Z1 square. Okay? Is it fine? So this is my earlier last day. Did you mention that was case 1? That is when we considered that. So this you can study, that is suppose case 1b. Okay. If we consider that is last day, what we learned, that is lambda 2 less than lambda 1 less than 0. So if you mention that one to be case 1, then this you can write case 1b. I am not writing case 2 because, like, to be fair with this notation, I am not writing case 2. Case 2 means when it is a repeated eigenvalue. At this moment, at least they are not repeated. Similarly, that is for other set of values, what you can have, that is z2, it can be minus 1 by z cube, okay, it can be even 1 by minus z1 to the power 4, so on and so forth, isn't it? Now, just you think about Charles Boyle's law, P equals to constant, right? So when we used to plot, that is, what was that axis? P versus V or V versus V? P versus V, right? So if it is pressure, if it is volume, we had this one where basically the nature is P is proportional to 1 by V. That was a hyperbola, rather rectangular hyperbola, right? Now you like think accordingly. That is, if you have a set of equation where you have, that is, y equals to 1 by x then y equals to 1 by x square, then y equals to 1 by x cube. What will be that? What will be those shapes?
Symmetric by 1.
It will be continuously get steeper and steeper, right? Are you confident about it? We will plot, don't worry. At least for one values we will plot. Now that is the thing we are going to do here. Okay? So let us draw the axis. Z1 and this is my Z2. Let us draw for the first quadrant, okay? Now, how could you draw? Again, we have to make that table, right? So, let us make that table. When it was a stable node, the nature was like that. Now, you are going to see that it would be I said that it would be unstable, it would be like this. So this will be the case. And now the case which we are dealing with, that is called a saddle point. Why it is saddle point? It will come clear. Okay. So it was for stable node. Now let's make the table. T and then Z1. Suppose it is my Z1 square and
So minus 1, minus 2.
because that's why that is first derivative square then 1 by square. Okay, in that way I am writing. So like starting from that is if I consider, see at this moment that is if I start from 1 then I won't be able to accommodate in this picture. So that's why I am starting with a low value. Okay, are you getting my point what I am saying? If I start with Z1 equals to 1, then of course that is it will start from 1. But last day, like in last case, what in case of stable node, what happened? That is it came down. So that's why that is like all the points I was able to accommodate within this section. But now they are going to increasing. So if I start from the same point 1 1, then what will happen? It will of course it will start from 1, then it will go like that. I won't be able to accommodate. So rather that is I am taking a point like somewhat here.
So then also it will go beyond the y-axis. So we have to scale the y-axis into 10.
That is fine. That is at this moment. That is what I am doing. I am trying to like draw the shape. For that, I need at least like 5, 6, 7 points. Okay. So that's what I am saying. That is from which point I can start.
Every point on y would be greater than 1. So on the y-axis, every point would be at least greater than 1.
Because the lowest point on x axis is 0.1. So 1 by 0.1 would be 10. So you can just write 1 instead of 0.1 in the y-axis. Then also it will be small, but then at least we will get 1 point.
Okay. So let us first make the table, and then accordingly I will scale up. Okay. So that is if I start. If it is 1. Although it is a continuous graph, okay, so that's why that is only after just getting the points we would be plotting only the one which would be feasible for us, okay. So if it is 1, then it is 1, it is 1, no problem. If it is 0.9, now you can say that is sir, why you were considering the same pattern for Z1, because you see here the lambda 1 that is less than 0. So what will be your value in that case? That is Z1, that will be e to the power minus t Z10. I am following that only. Now the change would be in the other thing. Change would be in the Z2. It would be what will be your Z2 now? That is Z2 equals to e to the power plus 2t Z2 0. But we are not taking this one because we will be using rather the other equation Z2 equals to c into Z1 to the power minus half. Okay. But your independent axis is the Z1, so that's why we have to like decide the values of the independent axis from this equation. So that's why again, while preparing this table, you have to list down the values of Z1. That will come from your first equation, e to the power minus t Z1 0. Okay, if you consider that Z1 0 to be like plus 1, then that is in the similarly that is 1.8, sorry 0.9, 0.8, 0.7. In that case, we have to do. Okay, so then it will be 0.81, 0.64. You get ready with your calculator. Let's.
The direction of in which the graph is moving, that we are getting from the first equation only, right? So why are we going on the point being the direction in which the graph moves, that we are getting from the equation e power lambda 1 t z.
That is true, but here that is why we are doing this exercise, because just to make our fundamentals or the basic intuition clear. Because first day probably you were not there on that class, that is when I directly from that slope I drew that one, then many of the students, because like you both had some knowledge because you knew the things, but who were the beginners, for them they were not at all confident when I drew that shape based on the situations, and then after that I decided okay, that is let us draw the locus on board so that it becomes really easy for all of them. That is the reason. Otherwise, you get readily. That's what that is at this moment. That is, I discuss this concept because ultimately it is going to be a different type of hyperbola. The shape will be like that only. But now that is just to reinforce our understanding. I am drawing this specific graph. Okay. Otherwise, this is the extra thing. Now, that is, please get ready with your calculator and tell me what will be these values, one by one. First of all, that is 1 by 0.81. সুতরাং আমি যখন এটা প্লট করব তুমি তোমার ওই যে ওই গ্রাফ প্লটিং ওইটা বার করবে করেছো দিয়ে এই প্রত্যেকটা তুমি একটু প্লট করে আমাকে দেখাবে তো কেমন আছে আমি এটা আগে করে নিই এক এক করে ভ্যালুগুলো বলো পয়েন্টের মিটি क्या क्या होगा हाँ अभी बोलो फर्स्ट वन 1.234 फाइन सेकंड वन 1 by 0.64 1.5 0.5625. Fine. Then 1 by 0.49, 2.024.
2.04.
Answer. Okay. Fine. Then 1 by 0.36. 0.777. Okay. 1 by 0.5, that will be 4, right? And then 1 by 0.16.
6.25.
6.25.
And then 10.
Oh, in that case, okay. That is, at this moment, if I have to draw that cup, I have to make it non-linear. Like the scale has to be. Fine.
So 10, 20, 30.
1, 2, 3, 4, 5, 6, isn't it? Because here, what is the value again? 1. I'm now like trying to draw 1, 2, 3 up to 10. Okay. You can think about it as if this is a scrambled or like compressed scale. Okay. Ultimately, the shape would be like that, but at this moment, I don't have that much space. But don't worry, that is, he is checking with a plotter, so that we can readily see. And at this moment, then please help me to draw the points. So if it is 1, 1, then 1, suppose it is starting from this point. After that, my 0.9, 1.234, 0.9, 1.3. Or something like here. After that, 0.6, sorry, 0.8, 1.56, 0.8, 1.56. Then 0.7, 2.04. And then 0.6, 2.707. Then 0.5, 6.
Aditya, sorry, but it's my class here.
Oh, sorry. We had in the.
So it was from 10:30 to 12.
Oh, okay. Sorry, sir. No worries.
Sorry.
Huh. Huh. For which one is the classroom for us for Friday?
You please complete whatever you are doing, we wait outside.
Sir, we are going to move.
You are recording ना?
हाँ.
आप थोड़ा अपना कंफर्म कर लीजिए कितना है अभी आपका 5 मिनट वेट करिए
ठीक है सर, थैंक यू.
2201 का खाली लगा
2201, हाँ. अरे I completely forgot today is Friday, no? Okay, first switch it off.
So can we request sir to take classes between 2201?
No, cannot be. Can you tell me the values quick? For 1, it was 1, right? For 1, it was 1. For 0.9, it was 1.234. For 0.8, it was
1.563.
for 0.7.
2.041.
For 0.6.
2.778.
For 0.25, it was 4, right?
Yes.
For 0.4.
6.25.
For 0.3.
Okay.
Okay, 1 by 0.3 square, I mean 1 by 0.09.
11.1.
Now that is if we join. You see exactly that is this hyperbola will come, right? And if you see on scale, now, can you show me that one? That is if it is.
So the direction is in that direction.
Here, could you please share that He is going to share the graphs on our Rovers Control WhatsApp group. All of you please open and check. This is for Z2 equals to 1 by Z1 square, and now that is I want you to check if it is 1 by Z1 cube, if it is 1 by Z1 to the power 4, so on so forth. And as I said, that it will be definitely that is the most steeper curve, so that's what Subrasham has readily found from a graph plotting software that is really very handy. So he is going to share and you please check. Then your concept would be complete.
So, so it will be, I think it will go progressively towards the right.
So it will start in the horizontal direction. It will start as the lesser power above, but in this direction, the lesser power goes to the left.
Are you saying that is it will be something like that?
Yes,
Yeah.
it will go to the right.
Okay.
Z1 cube, Z1 cube. Because if we
The
see
values would be higher.
Higher.
Okay, okay. That can happen. Yes. You are right. Subrasham, have you shared that in the group? All of you please open and check. Rovers Control was
Non-linear control.
non-linear. Okay. Sorry, non-linear.
network problem let me write.
अच्छा अच्छा
robust and non-linear.
all of you, that is, you see, that is in case of nonlinear, that is unless you check the graph patterns of the exam, use MATLAB or any kind of software. I mean, that is, you should see the like all the pictures and the graph. Otherwise, your basic intuitive knowledge will not develop. That is very much required, because in nonlinear the course is like that, not the course, basically the analysis. Every time you cannot do hand-driven calculation, or you cannot expect to find the solutions. You must have a definite sound intuition and the knowledge, so that like seeing the equation or by doing a minimum calculation, you must be able to like decode what is the underlying nature. That's what that is initially I am spending so much of time on the foundations or on the basics. But for that, like whenever there is, you will say, for example, this, we are now learning phase spring analysis. It will be your responsibility to check that using the software. Okay, not only the pattern of the graphs. If you take different type of examples, say for bifurcation on the other thing, you just for everything it is really easy. You either write a code or you use Simulink. Just it is a second order differential equation, two-stage, and then you check the XY graph. That will be your phase spring analysis. Okay, in Simulink it is very easy.
If you can laptops as well, great with class.
Although that is, we don't have a like lab component here, but that is the reason why I am drawing on board. Although it is like taking a lot more time, but it will help you to develop your knowledge. So now that is on the first day, if you remember, that is many of you asked that is how to decode the direction. That is here also the same thing. That is when I know my z1t, that is equals to e to the power minus t z1 0. So it will have the same pattern. Isn't it? Z1t will have the same pattern. So the values they are decreasing, right? Starting from the z1 0. So that's why we are going in this direction, because this is like z1 value is decreasing, and like for convenience I have chosen this one, so all the subsequent values would be less than 1. It's square, so it would be further less than 1, then 1 by that. So that's why the values are rising, isn't it? So already the z1 values they are less than 1, so z1 square, that would be further less than 1, and then 1 by z1 square, because your z2, that is c in this one. So that's why it is the rising nature, and the shape would be like that, or sorry, the direction would be like that, isn't it? Now exactly that is we have to find out the for other 3 quadrants. So exactly if you start from here, suppose if, so this is the point where I started, basically 1 1. So the axis, so this is the compressed axis. So this is 1 2 3 4 5 6 7 8 9. This is not a proper axis, but just to have the feeling that is what is the nature. In the same way, that is if we start from here again, if this is the point, then what would happen?
So the odd powers will not have graph in the second quadrant, it will have the third quadrant.
Right, very good. That's what that is we wanted to check, because here what happens, that is here for z1 square, z1 4 and z1 6, they will all be in the first quadrant, but the other ones not. Why? What is the reason?
Sine gets eliminated once you square it.
Because it is originally, if you see, the expression is there is z2 equals to c, that is 1 by z1 square, right? And last day what did I say, that is if you have any problem with respect to sine, then that is you go back to the original like solution of the differential equation, z1 and z2. So here z1 equals to the power minus t z1 0, z2 that is e to the power 2t z2 0. right? And now that is after that your Z2 equals to C, that is here Z1 to the power half C1 by Z1 square. Now that is we got some doubt regarding the values. Okay, let's see how we can resolve. That is, this is one case, and if it can be supposed, that is, if it is C Z1 to the power cube, then C1 by Z1 to the power cube. So we have got a doubt between the even power and odd power, right? Let's see, that is how can we resolve. At this moment, like suppose like Z1 0, Z2 0, both of them are greater than 0. If it is so, then what will happen? That is this, all this, like the Z1 square, here what did I say? That is, if Z1 0 is positive, then Z1t that will be greater than 0 for all t greater than equals to 0, isn't it? Then Z1 square that will be all positive, 1 by Z1 square that will also be positive, right? So there is Z, in that case it takes Z2, this will be greater than 0 for all t greater than equals to 0. Do all of you agree with that? We don't have any doubt. Then coming to this one again, Z1 0 positive, so Z1t that is also positive for all t greater than equals to 0. Then odd power of a plus number, what will happen? Plus. So 1 by that, still it would be plus. So if the initial condition is plus, then whatever may be the like power, like even power or odd power, I believe all of them would be on the first quadrant. The situation would be different, that is in this case, that is when we are changing one of the because you see, that is in that way we have to resolve. That is once again, even if it is Z1 to the power cube, but first you see that is what are the values of Z1. So as long as Z1 0 is positive, so Z1t that is also positive for all t greater than equals to 0. So that implies that is Z1 to the power cube, that is also 0 for all t greater than equals to 0. So 1 by Z1 cube, that is also greater than 0 for all t greater than equals to 0. Do you agree with that? Now that is the other case. If your Z1, suppose again the same situation, that is Z1 equals to e to the power minus t, sorry, Z1 0, Z2 equals to e to the power 2t, Z2 0, that we already have that one. Now Z1 0 is less than 0. Okay, so here we are assuming that is Z1 0 equals to minus 1, Z2 0 equals to plus 1. This is my initial condition. Now Z1 0 less than 0, that will imply that is Z1t that is less than 0 for all t greater than equals to 0. Okay? That implies Z2, that is C by Z1 square, that would be greater than 0, isn't it? So that's why that is I was about to draw like this, but not for all. That's what you want. Do you wanted to? Okay, that will be a good point. So is this fine? I need to erase some of the part because I have to draw this line. So okay, by the time you write, like let me see one other case. That is, if it is so, then after that, if my Z2 equals to C by Z1 cube, then what will happen?
If Z2 is positive,
No.
Z2 0 is positive, then
For negative,
if Z1 0 is negative and Z2 0 is positive, Z2 will always be positive.
Exactly.
C will be minus 1. No, C will become negative.
we are using the that equation, right? Z2 equal to C Z to the power minus 2.
The main equation, e to the power twice t z20. If z20 is positive, z2 will always be greater.
No, but we are not using the second equation.
No, no.
Relation.
I think the reason for the confusion is like, do you remember last day I said that is the Z2 was C into
Derived
C,
equation.
that is the derived equation, but these two are the basic. If you once again remember, that is we had the number 1 Z1t, that is e to the power lambda 1t Z10, okay? Then Z2t equals to e to the power lambda 2t Z20. Then after that, using these two equations, we got a derived relation, that is Z2 equals to Z1 to the power lambda 2 by lambda 1, where C equals to Z20 divided by Z10 to the power lambda 2 by lambda 1, right? So the fundamental relationship are given by the first two, and it's a derived relation. Okay, now that is, since that we have got a doubt, let's see. That is why both, what you said, both of you, that is what you are thinking, that is correct. But there, even like from the second equation also, we will reach the same conclusion. But there, the sign of the C also, that is what you said, sign of the C will matter. Like, let's see. Now the case is that Z10 is -1 and that is +1. Okay. So, and we are talking about, that is this. In this case, we consider the lambda 1 to be -1 and lambda 2 to be +2. That is the situation we are doing. So, sorry, +3. And at this moment, that is, we got a doubt what will be the sign of Z2. And if you see, according to this pattern, that is, we had Z20 that is greater than 0. So that implies, at least according to this one, Z2t that is greater than 0 for all t greater than equals to 0. But now, that is, you are not convinced because mismatch. Or rather, I should say apparent mismatch. What is the reason for apparent mismatch? Because here the Z1q, when it is there, at the same time it will imply, that is, if my Z1 less than 0, it will imply that I am writing all the lines so that you do not have any doubt. Okay. This is also Sutashum, that is, you thought in this direction, that is, this is negative, means the odd power will of course be negative. Now, if that is the situation, then whether that it is negative or positive, that is our question. Now, here, that is the decision maker is C. Now we have to analyze the C. Let's see, that is what is the situation. Z20, that is my +1. Yes, fine, that is +1. Now Z10, that is -1
-3 to the power -3.
to the power -3. So ultimately what will happen?
-1.
So that minus and the minus of Z1q together, it will make it plus. So that's why, that is, if you remember, maybe last day I said whenever you have a doubt regarding this sign, because this one is a derived relationship, from that it sometimes be really confusing or really difficult to derive, to find out the actual sign. So whenever that is you face any confusion regarding the sign, you go back to the first two, that is the solution to the differential equation, and as I said, that is the sign of Z1 and Z2, that will be completely governed by the initial condition. Why? Because e to the power something cannot be negative, right? like e to the power plus something or e to the power minus something, that can ever be negative. So that's why the sign of the Z1 and Z2, they are entirely governed by the by the initial condition. And whenever that is you got any doubt regarding the confusion, always you go back to the first two, because the reason for that is that the third one is a derived relationship. Okay. So that's why that is when we go for here, that is the initial condition Z10 is negative and Z20 is positive, whatever may be the power, the family of graphs, they will all be in the second quadrant. Okay. Similarly for third quadrant and fourth quadrant as well. It has been really a very good discussion, and thanks to both of you, because if you wouldn't have asked, then we wouldn't have discussed this, and then maybe this confusion would have been there in your mind. If you start from here, then what about that table? Z1, then Z1 square, and then that is 1 by Z1 square, right? Although all my Z1 is negative, so if you see the table, then what will happen? That is Z1 square, Z2. So this is starting from -1, minus 0.9, minus 0.8, minus 0.7, minus 0.6, minus 0.5, so on and so forth. But as I am taking square, so then what will happen? All those values will still be positive, right? And then Z2, which is C by Z1 square. Then accordingly, if you consider C to be 1, all of them will remain the same positive values, right? Starting from 1, then after that 1.2, 3, 4, and then for 0.8 it was whatever with all the same values with the same sign, right? Only the change is that is here we had all the positive set of values, now we have the same magnitude but with a negative sign. So starting from -1, that is if it is starting, if suppose if this point is -1, then after that minus 0.9, minus 0.8, minus 0.7, so on. Now the movement is going to be like this. Do you agree, all of you? Why the arrow is in this side? You see this pattern. First -1, the next point will be like -1, +1. That is the first point. Then -0.9, plus 1.234. The third point will be -0.8, that is 1.577, something like that. So the arrow will be this word. Is it clear for all of you? Everyone please check. If you have any doubt, ask me. Now, if it is on the third quadrant, that means after this, if I consider Z10 equals to -1, Z20 is also -1, then what will happen? The first point here, what did I say? It was -1, 1. Okay, now that is if I consider exactly this point. What is that point? -1, -1. I'm talking about this point. Okay, maybe with the white choice. Now, what is the situation? If both the initial condition are minus, then Z1t that is less than 0 for all t greater than equals to 0, as well as Z2t that is also strictly negative, right? For all t greater than equals to 0. But once again you see the numerical values, I mean the absolute values, they don't change. All these like 0.8, 0.9 and then here 1.234, all the other values, only their sign would be entirely different. But their magnitude, the absolute values will remain the same, right? So then what will be my point? First -1, then minus 0.9, minus 1.234. Third one -0.8, minus 1. What was the third value? 56. So then can't we say that is it would be something like that? Manish, is it fine? Ashutosh, is it fine that is in the third quadrant this will be the nature for all of you? Adino?
Yes, it's clear.
Arup? And then if it is in the fourth quadrant, that is if I start from this point, what will be this point? This is plus -1. So here entirely all the Z1 values are positive but Z2 values are negative. Once again, the magnitude will remain the same. That means absolute values, numerical values will remain the same, only the sign will be different. Okay. Then once again, what will be the pattern? Again, like starting from 1, -1. Then plus 0.9, minus 1.234. Third point, plus 0.8, minus 1.577 maybe. So then once again, do you agree? The pattern would be like this. So it is diverging nature. That is the reason why we call that this is a unstable, like this, as a whole this is called a saddle point. Why saddle point? That will be clear to us because we haven't yet drawn the graphs for the axis. Okay, after that it will be clear why this is called a saddle point. But anyway, as this gives the diverging nature, that is clear to you. That is the reason why in this case it is an unstable. Here you might say that sir, if one of the eigenvalues is positive, then of course it would be unstable. Then why do you at all need to study this? Because when we learned the stability for LTI systems, we had a notion that is if we find that is even if there is one pole is on the RHP, unstable system, uska kuch nahi hoga, chhod do. So, but here why we are still learning it? Because it may happen, that is basically there is a nature for simple pendulum, that is here, if a nonlinear system has multiple equilibrium points, suppose you have, that is the first one, that is you have two stable foci and in between one saddle point. That is the very common type of nature. So for that actually that is we are learning. What I meant to say, it can happen that is suppose 0, 0, that is a stable focus. Okay, now here you have one point which is plus pi comma 0, that is a saddle point. Here also you have another that is minus pi comma 0. This is plus pi comma 0. Sorry. And here the nature is something like that. Don't draw. I have to. Are you getting the shape? For the simple pendulum, we have multiple isolated equilibrium points as given by that is in pi comma 0 for simple pendulum. So that is here you have 0 0, then plus minus pi comma 0, then plus minus 2 pi comma 0, so on so forth. Then 0 0, this one is a stable focus. The nature we will soon learn, that is a stable focus means logarithmic spiral inward. Okay, once again, logarithmic spiral inward, like shape is something like that. This is called stable focus. So 0 0, it will be a stable focus. Again, plus minus 2 pi comma 0, that will also be stable focus. However, the between points, like in between, plus minus pi comma 0, then again plus minus 3 pi comma 0, they will all be saddle point. Saddle point is unstable in nature. Now, what is the interpretation? You finish writing, after that I will say. This is for the exactly. This is for like x1 versus x2. x1 is theta and that is x2. That is my x1. So if it is for simple pendulum, x1 is my theta and x2 theta dot. Yes, Manish, you are correct. So now what is the interpretation? Like earlier, all the green boards, that is, if I do like this, then there will be completely a nice pattern. But here it is on the blackboard, I am not able to do that. What does it mean? Everybody please look at the board. This hatched portion, like roughly, this will be the region of attraction for this equilibrium point. I mean, if the initial condition is within that zone, supposing the point is here or here, ultimately that will come down to this point. But as much as it is close to that separatrix, that is, it is as if the boundary to the zone of the other equilibrium condition. Suppose if it is like this, then of course it will go there. If it is there, of course it will go there. If it is here, of course it will go there. That is the interpretation. So once again, this is the case study for simple pendulum. It has many isolated equilibrium points. They are given by n pi 0, n for n natural numbers, 0, plus minus 1, plus minus 2. So, and what will be the nature? That we can easily see. In fact, we will see after this. 0, 0 is a stable focus. Okay. Plus minus pi comma 0, that is a saddle point. So here minus pi comma 0, you see the saddle point, the nature that I have drawn here also the thing. After that, although I didn't draw it at this moment, plus minus 2 pi comma 0, that means after that, another stable focus. That means if some equilibrium point is there, it will go and come here. So here it will be plus 2 pi comma 0. Similarly here, it would be minus 2 pi comma 0. Suppose something, if the equilibrium point is here, so then that is, it will go like that. So it will be minus 2 pi comma 0. Similarly after that, it will be plus 3 pi, minus 3 pi comma 0 plus, it will just go on, so on so forth. Okay. Now that is this zone. See, here you have a separatrix, right, with respect to this line and this line, as if this is diverging but towards this region. Right? Here also this is diverging to another equilibrium point. So as a whole, all of you please look at the board. As a whole, if you think about this zone, then that is called the region of attraction for Z00 point. That's why I have drawn all this line once again. That is with respect to this border line, with respect to this border. If you think in that direction, like this, so all this area which is in between my arms, that will be the region of attraction. That is the meaning. If your initial condition is within that region, then it will be attracted or the system motion will go to 0, 0. But as much as it is like, close to that boundary, or maybe these trajectories are called separatrix. Separatrix means which separates two regions. This is one region, this is another region, because this is a stable region, this is an unstable region. So as much as the equilibrium point moves towards this, so then it will be attracted to the unstable equilibrium point. Here also, the same thing. So this is about the phase plane analysis, and for that actually we are doing so much of exercise. We are learning it for LTISS, but ultimately we will have to analyze this. If you see Khalil's book there, you will have two examples. There is one is the two case study basically. One is the simple pendulum, another one is the case study for tunnel dam. For both of them you will find that is it will have multiple accelerated equilibrium points, and then depending upon the region of attraction or like depending upon the zone of the initial condition, it would be either a stable operating it would be either a stable equilibrium point or it would be unstable. Okay. And for any nonlinear system, in this kind of thing, that this is for second order, so that's why we have a very visually appealing graphical interpretation. But for higher order system, we won't be able to draw it like that. But by analytical calculations, that is, we can find out the region of attraction, and then you have to design the controller so that it can keep the system within this zone. Do you remember? That is why a few minutes ago, like Faz was asking, sir, what would be the nature of the controller when applied to a nonlinear system? That the responsibility of the controller will be to confine the system within the safe zone, because we know that is if somewhat it goes beyond this region, then even the controller will not also be able to, that is, bring back the system to the stability. Are you getting? That is in case of nonlinear, depending upon this, like the region of attraction, the controller has to like take care of this fact. That is, it will always try to keep the system within this zone, because once if it crosses that region, then that is it will not only that is it will enter into the unstable region, the controller will not also be able to bring it back. So that's why that is it is like much more difficult to control the nonlinear systems compared to linear ones.
So, suppose if there is a system that keeps on jumping between a stable and unstable equilibrium point.
That automatically that cannot happen, right? Either there will be a parameter or it will be subjected to the input.
So, even in one of those cases, if it keeps on jumping between two stable and unstable equilibrium points, so the region of attraction will keep on changing also.
No, but for a like if the system originally has that kind of nature, like automatically it cannot happen. As I said, that is either there will be a parameter which is responsible for that, like the to and fro change between the equilibrium point or the input. But in practical cases, that we have to stop that kind of situation.
So if that kind of situation arises, we will not be able to design a controller for this.
Why not? That is, we have to then design the controller so that it will be kept in one region only.
So first we'll have to stop that nature and then you can design, right? You cannot design it when it's fluctuating between.
No. That is for we have to first find out the reason for which it is changing. That is, suppose of course there will be either, as I said, either a parameter or depending upon the input. So first we will have to find that is what is that factor which drives the system from one zone to another zone, and then that is we have to design the controller so that it doesn't allow that parameter to go into that segment or range which causes this change.
So in that case, how will you first of all come to know that what region of attraction the controller should function at?
I can give one example, that is these power electronic converters. Say for example buck or boost, maybe that is under second or third day, that is I drew that structure. Simply a buck converter, that is a step down chopper, switched linear systems. For certain input or for the gate pulse, if it is 1, then the switch will on, it will give you one particular structure, okay? And for switch off, it will another structure. In both the cases, the operating point will also be different, but both of them would be stable operating points, okay? Now, what is about the operation? That is, if you have a DC-DC converters, then which is called a step down chopper, for that ultimately the output voltage is the average over the VT. So in that case, that is, what is that situation? Just this is an interesting example. That is for any kind of converters. I hope all of you know about the DC-DC converters, like step down chopper or step up chopper. Simply suppose if the voltage, if it is like this, suppose the voltage it is going pulsating voltage. It can be either this, it can be either this, even it can be like this. If this is the, if you have a like pulsating waveform, then ultimately what will be the average? Right? For a DC-DC converter, that is this V output equals to duty cycle D into V in. Okay. Now suppose the input voltage is 24 volt. Okay, the input battery is 24 volt, and you would like to get an steady output voltage 18 volt. So 24 volt, that is V in, and from that you need a steady voltage of 18 volt. So what will be your D? It would be like 18 by 24, right? It will be 0.75. Then that is, this is the example where in some part it would be T on, and that like if the duty cycle is 0.7, isn't it? In that case, the duty is 0.75. What does it mean? If the T, suppose if the T is 1 second, then for 3/4 time it will be on, and 1/4 time it will be off. So this is T on and this is T off. Similarly, it will continue. This is the pattern of the gate pulse. Like after this here, do something like this. This will be pattern of the gate pulse. Okay. Now for the T on, there will be one stable equilibrium point with respect to which the system operates. During T off, there will be another equilibrium point which is also stable. I mean, quantifiers was asking that is, can we have a system where we will have two stable equilibrium points? Then I like told him that is yes, that is possible in some particular cases, but of course it cannot happen on its own. There has to be an external influence under which it can be there, because if you have two stable equilibrium points, the system cannot autonomously move from one stable equilibrium point to another stable equilibrium point. Of course, there has to be a forcing function. So here, forcing function means the gate control. When it is T on, you have one specific arrangement, you have one equilibrium point which is stable. During T off, you have another, because it is a switch means of course it will be another linear circuit. Both of them would be RLC circuit, but it will be, when we discuss the variable structure systems, there I discuss this one, right? So for T on, that is for switch on, you have one circuit, for switch off you have another circuit, and the transition is happening because you are applying this type of gate pulse to the switch, right? And ultimately your voltage would be the arithmetic average of this AC signal, because ultimately whenever it is a switch circuit, you cannot expect the output to be DC, like perfect DC. Of course it would be pulsating, and then we have to consider the average. Anyway, the point is that in case of this power electronic converters, you have like two stable equilibrium points, that is one corresponding to T on, another one corresponding to T off, and we are forcing the system to jump between these two stable operating points, because of which ultimately you will be getting the averaging. That is the application. But if you see, that is, as I said, that is like you were asking, that is if it does so on its own, that is not possible. Because the basic nature of any physical system, every physical system has this inertia,
So it will always try to be there at some point unless it is unstable. Now power electronic converters, they are stable in nature, RLC circuit, right? And not only stable, they are asymptotically stable. So individually, if you see those two configurations for switch on and switch off, they are asymptotically stable. So if our system is asymptotically stable without a forcing function or external influence, it cannot change its equilibrium point. And here we are purposefully doing that because ultimately this operation is required, sometimes on and sometimes off, so that ultimately there will be an averaging. If you need more output, then you have to increase the T on, right? Are you getting? That is, if you need the more output, suppose if the duty ratio is 0.5, you want only 12 volt, then it would be 50%, 50%. That means half T on, half T off. But if it is 0.75, that means you have to keep the switch on for longer time. So that is a perfect example. That is where we create this type of situation where we force the system to switch from one equilibrium point to other, rather we should say operating point, because this is forced, right? So we force the system to just change its operating point, and that too for a purpose. It is not that like without any reason we are doing it. Suppose if it is there continuously T on, then what will happen? And the output also you will be getting 24 volt, no reduction. Or if it is switch off, then in the output you will be getting 0 volt. Here this buck converter means it's a DC-DC chopper. You heard about transformer steps up or step down voltage. So this chopper means it is a DC, it is analogous to a DC transformer. Because in DC transformer doesn't work, so we use this kind of semiconductor devices or power electronic devices for stepping up or for stepping down a DC voltage. So here, like from 24, we are reducing the voltage. That's why it is called a step down chopper, whose commercial name or the technical name is a buck converter. Okay, if it is step up, that is called a boost converter. They are also the same thing. That is how much you want the voltage to be. You have to decide the T on and T. So once again, corresponding to T on, you have a stable equilibrium point or stable operating point. Corresponding to T off also, you have another stable operating point. And we force the system to switch back and forth between these two, so that ultimately we get an average of the value. If we don't change the switch, then the averaging won't happen. So it would be either equal to V in or it would be equal to 0 for all time, but that is not desired. Okay. So now that is one last bit. Can you tell me that is what would be the situation for the 4 axis? If it is 1 0 and then 0 1 minus 1 0 and then 0 minus 1, that we need to decide, because otherwise we won't be able to understand the meaning of saddle point. So suppose that is here, if somewhat, if we take this point, this point, this point, this point and this point, what will happen? Similar to the last day's analysis, if one of the initial condition is 0, then how will you decide?
Horizontal line converge towards the center through the line. Z1.
Just very easy manner how we can do it. Suppose my Z10 that is positive, but Z20 equals to 0. That is my case. Then what will happen? Z1t, that will be e to the power minus t Z10. That will be decreasing value. But what about your Z2? Because Z2 means that is e to the power plus 2t Z20. Although it is an unstable mode, but at least in the coupled system, if the initial condition is 0, then Z2t equals to 0 for all t greater than equals to 0, right? So then what will be the locus? Starting from, if it is z10, comma 0 and z10 the value is decreasing towards 0, then what will happen? Isn't it? Are you getting? Z2 is continuously 0 for all t greater than equals to 0, and Z1, that is starting from Z10 the value is decreasing. So if it is a Z10, then in which direction it will go? Towards the origin. Now the same thing, that is if there is Z10, if it is less than 0 and Z20 equals to 0, then what will happen? Exactly the same thing. Starting from a minus value, say for example -1 or -0.5, then it would be all that is going towards the origin, because the value would be like the magnitude would be decreasing. So starting from here, don't we see this one? Because what will be then the value of Z1? This one? This is Z1, this is T. This is minus Z10. Or rather you can write Z10 which is -1, then gradually it will go towards 0. -1, -0.9, -0.8, but Z2 it will imply continuously 0. So it will follow this line only towards the origin. Now if the other situation, Z10, 0, Z20 greater than 0, then what will happen? Once again, we cannot use that relation Z2 equals to C Z1 to the power lambda 2 by lambda 1, right? For the same reason. Are you getting what I am saying? The last day also what I said, that is if one of them, that is now Z1, that will be 0, so it will come down, so it will be undefined, so we cannot use the third relation. We have to depend upon the only the solution. Then what will happen? Z10, that will imply Z1t will be 0 for all t greater than equals to 0. Okay? And what about Z2t? It will be strictly increasing, because Z2t, that is e to the power 2t, Z20. So this is strictly increasing. So then if this is the point, from that it will continuously go upwards. Diverging nature. Is it fine? Starting whatever may be the value of Z20, like then what will happen? That is, if this is Z2 and if this is T, then it will be like that. That this is my Z20 and this will be the values, continuously growing values. So it will go high and high, okay? Similarly, if it is there, it will be with respect to the negative values also it will be following the continuously this axis. So that's why this gives you a stable attracting nature. I mean origin is still the equilibrium point. If you see these two lines, they are approaching the origin, that means converging nature, but after that immediately they will diverge. That's why in this case it is called a saddle point. Saddle point means after reaching that point there will be an abrupt change in the characteristic. Once again, these two you can see they are approaching the origin. That means stable nature. But immediately once they reach, after that they will diverge. Once in this way, another this way. And all the other patterns you see in this way, this is going upward, right? So you see that is all the directions, they are also following them. That is here it is following, it is diverging. Here also it is diverging along this. It is diverging along this. It is diverging along this. So this is called the saddle point equilibrium point, which is unstable in nature. Although momentarily you may think that is okay, if my initial condition is like that, then it would be stable, but no guarantee that is initial condition, that is that Z2 will always be 0. The moment Z2 takes a positive value, वो थोड़ा थोड़ा करके unstable हो जाएगा.
So that will require a forcing function, right? Because once the two states become zero at the origin.
No, actually, this is the pattern. It depends upon the initial condition, right? That is here when we are drawing the line only on the Z1 axis. We have assumed that is the Z2 0, like Z initial condition of the Z2 is completely zero.
So once it reaches the center, it won't just go up or down on its own. We have to.
Because why I am saying, because ultimately you would be operating it under some forcing function. So then the motion would be like that. And here also you see this attracting nature is only for when Z2 equals to 0. Only under that constraint that your Z20 is 0, it will give you a converging nature. But the moment you have even a very small Z20, then थोड़ा थोड़ा करके वो unstable होगा. That's what I said. So that's why that is this saddle point. This is also unstable nature. And when I drew it, now could you see that is here that this is please correct it, okay? Because earlier there is arrows were not exact, because this means, see, that is this is the one of them would be like stable, another one of them would be diverging. So here if it is something like that, it will go towards this, further this, but in this case, because if it is there, then also it would come back. That's why this arrow should be there. Earlier I gave the arrow like this, but in that case, if the point is here, then it will not come back to this point. That's why the arrow needs here. Here also you can see that is all the different pattern. That is here it is diverging, so the remaining curves are following that. Okay. Okay. Thank you. Here also the same thing. This is going towards this side, and this must also have. One of them would be attracting, another one of them would be diverging. Like here also. One set would be attracting, another set would be diverging. Like here, if you have a point like this, then also it will be going like this. But if the point is in this region, then what will happen? That is gradually it will come here. Is in diverge. All this, that is, once you simulate that and you take different initial conditions, it will be perfectly clear to you. But at this moment, there is everything I am like guiding you. That is okay. It will go in this direction. So that's why you still have some confusion. But you have to simulate it. In simulating it is really easy. Okay, that is we are stopping. But these are all the fundamentals. Okay, so that's why again this for saddle point also I developed the things from scratch, and then again everything we learned. You should check on the book, and like in between if you have any doubt, you feel free to ask.